font visible to everyone? Yeah, it's the same as before. So the starting part of this code is very similar to what we did last time, right? To generate a positive definite matrix. Okay, so that for those of you who have forgotten, it's just that I've created a symmetric matrix by starting with a random matrix. This was a random matrix. I made it symmetric. Then in line 10, I looked at its eigenvalues and I made them some random integers so that they became positive definite. Okay, and okay. And then I reconstructed A matrix as V diagonal eigenvalues V transpose. Okay. Then there's a random B vector which is the right hand side of my problem. So Ax equal to B, my A is ready, my B is ready, I'm ready for action, right. This was the quadratic function as I showed you last time. This is how you define a function in terms of x, right. So half x transpose Ax minus B transpose x. That is my quadratic function. I have the gradient which I've written as a function. Okay, and so let's actually run this part. Okay, so A is done. Now I'm going to prepare the function. Okay, and this was gradient descent. Okay, 50 steps. So we can run this as well. So this is the convergence of steepest descent. Okay, I don't know why it is called LS. Anyway, now we are looking at conjugate gradient method. Conjugate gradient method, my starting point is some x naught which I defined earlier on, same x naught, right. Once I know my x naught, I can immediately calculate the residual because that's simply Ax minus B, right. Ax minus B is the same as grad f. So I use R as grad f x. Okay. So what am I doing in these steps? I'm defining all the initial parameters to enter inside the CG loop. Initial parameters is that the conjugate direction P naught is minus R, so that's taken care of here. This x underscore CG is just for me to keep track. Ideally I should not be storing all of this. This is just so that I can do analysis later. Okay. I just read this is GF. I'm storing it. I need not have stored it. Okay. Now the logic for the conjugate gradient method loop is the same as before. I'm going to say while the norm of the gradient is above some tolerance, tolerance is some low small number, okay, maybe 10 to the minus 12 or whatever, and less than the maximum number of iterations which I decided. Okay, I have an expression for alpha, the simplified expression for alpha, right. Remember that R is correctly populated at R0 when I enter this loop. So my alpha 0 is correctly done. Once I know alpha, I already know P because I've entered the loop knowing P. I can calculate my x new. So I got my x new, right. Once I find out my x new, I should be careful. I should not jump into the next loop without updating what? My P and my beta. So far I have not used my beta. Okay. Now I write down my R new. Okay. R new, we derived this over here. Rk minus 1 was simply in terms of A times Pk, right. So I get this. Similarly, now I use my expression for beta. I get my beta is ready. Once my beta is ready, I get ready and prepare my P for the next time I come back inside, because you notice the first step of the loop is to calculate my alpha, for which I need the P to be the correct value. So I got my P from here. I update my residual once again, right. This part is just keeping track of how well the norm of the gradient died down, etc. So that's why I'm calling it bookkeeping. Okay, and it will show me a iteration count every time. Having done that, it's just going to plot all of this and show me, right. So what we saw here was in the case of steepest descent, at 37 iterations I got down to norm grad is about 10 to the minus 7. Now let's run this section. You notice what happened? 9 iterations, it's down to 10 to the minus 14, right. That's machine precision. And look at this. Note, so the red curve is the progress of norm grad f. I'm plotting in log scale so that I can make better sense of it. So notice how leisurely steepest descent walks, right? At the end of 50, not 50, 37 iterations, it is reached the log value of 10 to the of what, minus 14. Whereas this guy within the 9th or 10th iterations is down to essentially close to machine precision. Okay, so this is telling you that conjugate gradient method is much better than steepest descent over here. And here I'm just plotting the eigenvalues. Are there any repeated eigenvalues? Right, so 9 and 10, the eigenvalue is the same, 17, which is why I finished in 9 steps. Right, one repeated eigenvalue gave it to me, and I didn't plan this, by the way. It's the random integer. It so happened that way. Okay. So let's. So any questions on this? Anything that we should try next? Correct. Okay. If you so you want to make tolerance something even smaller, or remove it. Okay, fine. Just remove it altogether. Okay, so let's do that. That's what you want? Okay. So now let's. Okay. So what it did was, this is the entire trajectory. So it reached over here. Basically, it reached the solution. So this is xk minus x star. How far am I from the solution? So I started making progress in CG, reached the final solution now at the 10th step. And then what happened? I'm just wasting time, basically. From iteration 10 to 50, I'm wasting time. So it had said at most 10 steps. It worked in at most 10 steps. Are there any repeated eigenvalues this time? My random integers turn out to be all distinct. So it took me 10 steps and I reached the solution in 10 steps. After that, I just basically wasted time. Okay. So if you look at the here, the actual values, they're all the same. And it's at basically at the 10th step when I hit this, and then I'm just fluctuating. These are all insignificant fluctuations because it's in 10 to the minus 14. Okay. Anything else that we want to try? Why don't we, okay, so let's get this guy back. We have a few other interesting types of eigenvalues to try. So let's try that, right? So let's try something like this. So I have how many distinct eigenvalues? 1, 2, 3 distinct eigenvalues, right? 1, 5 and 10. A very artificial problem, but let's see what happens. So eigenvalues are 10, 5 and 1. How many steps did I take? I essentially, yeah, this 3.5 and all is just a plotting artifact. It's not actually 3.5 iterations. So at the end of, at the 4th iteration, basically I've reached my solution, right? So 3 repeated eigenvalues took, then it just took 3 steps to reach the solution. And you look at the convergence plot, it's huge, right? So this is kind of proof that short-term gain, ideas based on short-term gain don't always pan out, right? When we came up with steepest descent, it looked like this is the smartest thing to do. Just keep going in the negative gradient, I'm going to do well, I can't go wrong. Well, look at the top left plot, right? Steepest descent is in this way, going 50 iterations, it's down to minus 10 in the log. This guy is down to minus 30 in the log within how many iterations? 4 iterations, right? Okay, at best it will take 10 iterations if the eigenvalues were truly random, okay? So the more information you know or can get about the problem, the more fine-tuned a solution you should choose. So supposing your physics-based problem gave you some knowledge that the eigenvalues are going to be clustered around something or they're going to be something, then you should use a method that can leverage that information. It turns out that the conjugate gradient method is leveraging repeated eigenvalues in a very, very nice way. Of course, we haven't proven this. This is that same person, Loonberger, who has another book on optimization who has proved this, but we are not going into it. Okay. All right. Any other experiment anyone wants to try? All are same eigenvalues. Okay, let's go back to that. Let's say 7, okay? Okay. I basically, it took me one step to get there. But what happened to steepest descent? Steepest descent also took one step only. Why? Why is the first step the right step? Because it's a circular thing, right? So wherever you go, you are looking directly, steepest descent is directly taking me to the center, right? So that's what it is. In fact, what we have solved over here is actually a very, very simple problem, because what will A matrix actually be? It's V lambda V transpose. Lambda is 7 times identity, take it out, what am I left with? A is the identity matrix. I basically solved my solution x equal to b. If this problem was solved by a human instead of a computer, we would beat the computer by one iteration, right? I mean, i.e. no iteration. Okay. All right. Any more challenging problem to try over here? A large condition number. Very good. Okay. So let us try this one. Okay. Highest eigenvalue is 1000. Okay. So what happened to steepest descent? Steepest descent died, essentially, right? Conjugate gradient method still survived, right? It has reached, so if I look at x minus x star, it has reached, it's essentially reached in the, this is in the log scale, it's reached, right? If I look at the residual over here, 10 to the minus 13. And 5 iterations, because there are 5 distinct eigenvalues, 1, 5, 10 and 1000, right? And here I have reached. So if the eigenvalues were not distinct, it would take 10 steps. If there were 10 distinct eigenvalues with a bad condition number also, it's working well. We can get even, let's get even greedier. Okay. At some point CG should also break. Well, at this point it has not. But CG has done something strange over here. Right? Of course, our steepest descent died much early on. Conjugate gradient method has reached a stationary point, which is evident from the fact that xk minus x star has also gone in the log scale to 10 to the minus this thing, right? There is something strange that has happened here. So this actually is going to motivate what we will do next. The way I have implemented CG in this module is, you would never implement CG in this way in real life. What I've shown you is a textbook implementation. Why? Because this is not factoring for a bad condition number. Okay. So there is a cousin of the conjugate gradient method called the precondition conjugate gradient method, where you try to fix this condition number problem. So we will come to that next. So if you take any real life implementation of CG, no one would write it the way I did. They would do a preconditioning and then run it. So we'll look at that next. This is purely due to numerical issues. The condition number is what is messing you up. Okay, so that's about it in terms of what I wanted to show you about the conjugate gradient method. So you have at your disposal now 2 solid techniques. You know steepest descent, you know its linear convergence. You have conjugate gradient, which has also linear convergence but much faster over here with nice properties, right? So you can actually begin applying this in your research problems or whatever. You know, it would be better to wait for the preconditioning so that you get even more robust behavior depending on the condition number. Okay, and after that we will see how we can take this linear CG method and adapt it to a non-linear problem, which is very, very powerful. Okay, you can do the same thing with steepest descent also, but CG works better, like how it worked here. Okay. If you will it work better, you mean? How will the algorithm get modified if I have a regularization? So if the regularization is a very nice regularization in the way that I can write it once again as half x transpose a dash x minus b transpose x, then it will basically go the same way. If you cannot write it in that simple way, then we'll have to probably take the nonlinear version of CG. Okay. Yeah. The nonlinear version, we'll come to it, is also very straightforward, so there's no problem over there. In the bottom, I believe it is log. We can just confirm it. Yeah, it's log. So this is log for steepest descent and CG, and yep. I'll upload this code as before, and then you can see it. Yeah, here you go. This is actually what it is. So log of xsd minus x2. So these are just some bells and whistles if you want to have your legends have LaTeX font in it. Okay. When you have too much time, you do these things. Okay. But it gives you good graphs. So as you read this, one suggestion to all of you who particularly who are somewhat new to MATLAB, go through this code. It's a simple 100-line code. You should understand every single command that is happening over here. You should know it, you should internalize it and begin using it in your work, right? So for example, what is repmat? Does anyone know what is repmat? Replicate a matrix. Okay, so small tricks like this so that you avoid writing loops. Okay. How does? We haven't actually implemented any CDM here, so it should look similar because it also has the property of at most n steps. But for CDM, then you have to tell me how are you picking the p's. So let us say you chose to do the eigenvalue decomposition. You can do it. I suspect it will look very, very similar. The only difference between conjugate gradient and conjugate direction method is that you don't invest that cost in evaluating the p's. In the case of the conjugate gradient, you're starting with steepest descent and then building up step by step. It's iterative that. So I don't need P100 until I come to step 100. Whereas when I do eigen decomposition, I calculate all of them beforehand, whether or not I need it. The trajectory will qualitatively be the same because the directions are different. Right? There, nowhere did we claim that the conjugate vectors that I got now are eigenvectors. So different. It is going along different directions. Yeah. about its descent, whether or not it's a descent direction. Well, we kind of did, in the sense that, remember we said that if when you look at the expression for alpha k, if it is not a descent direction, alpha k becomes negative, right? There was a RK transpose PK in the expression for right here, right? Alpha has, okay, not here, in the original expression for alpha, there was a RK transpose PK. If it is a descent direction, that became minus, and there was already a minus sign, so it became positive, okay? However, if it is not a descent direction, then alpha will be negative, right? And that seems like a problem, but the expression for xk plus 1 is xk plus 1 is equal to xk plus alpha k pk, and alpha is turning out to be negative. Instead, now I replace pk by some new vector which is equal to minus qk, which is now a descent direction, and it is giving me a positive step length. So the progress happens in the same way. If it is not a descent direction, if pk is not a descent direction, that means it's an ascent direction. I get a step length which is negative, which means effectively I'm still descending. So I am in some sense always descending. So all of them are descending. The only difference is the trajectory in which I descend. Do I go in a zigzag way, or do I go systematically along the axis directions and reach the solution? That's a good question.